Hello. Now I'm going to apply the two-stage regression, two-stage estimators asymptotic results to the two-stage least square estimator for the IV regression model. Right? Complicated there are. So we learned IV regression model earlier in chapter 2, and in the previous video we learned the general asymptotic derivation for any kind of two-stage estimator. Now we are applying the two-stage estimator to the IV regression model, and we already learned the fitted value approach. That is basically the two-stage approach. So I'm going to present the simplest possible case to help you intuitively understand what happened. And then later I'm going to present, maybe in the next lecture on Thursday, I will give you the general case. So let's start from the simple scalar case. Y is determined by a linear function of x, and y is scalar, x is scalar, one dimension. Of course, beta is scalar, epsilon is scalar, and also x is endogenous, so it's determined by gamma z plus psi. Everything is scalar, and obviously x is endogenous, z is instrument, and I will assume that all the random variables have mean 0. So you may understand x and z as demeaned variable. So if you want, you can introduce the intercepts if you want, but I will ignore them. And then we know how to estimate this. So it is pretty straightforward. You can estimate gamma first. So it is simple OLS regression model. So classical linear regression model. And you can estimate gamma using the OLS method. And then from the gamma hat, so gamma hat is obtained by this principle, minimizing sum of squared residuals, and then its first order condition is given by this form. It is a kind of moment condition, or we use this because this is the starting point of the asymptotic normality we derived in chapter 3. So as you remember, we Taylor expand this function, and then everything starts. So this is the important function, or you may understand it as a moment function. Anyhow, you know how to handle this. It is a simple OLS method. And then, now let's think about how we estimate beta 0. Remember how we identify beta in the fitted value approach. In the fitted value approach, we replace x with gamma z. So we are going to excuse me. So this is the first stage. I did not finish the first stage. So the first stage theory is implied by the theory we learned in chapter 3. In chapter 3, as I explained, from this function, you Taylor expand that function to a linear function, and then apply some convergence theorems. Then you obtain asymptotic normality. That's what we did. Through the same procedure, you have some key functions like this: derivative, simple, and the influence function we derived in the previous video is given by this. So as a result, at the end, this is what you get. So the influence function is defined in this way. So this is the contribution of individual I on the estimation error. So if the error term is large for ith observation, then the estimation error will be larger as much as this term, right? And then, okay, now let's go to the second stage regression here. The second stage regression replaces x with gamma z. You may remember the fitted value approach. So based on this fitted value approach, this is our minimization problem. We regress y on gamma z. Of course, the error term changes, but the point here is we are going to minimize the sum of squared residual of y minus beta gamma z. So this, remember, this is this sum of square includes beta and gamma, but this sum of squares is for beta. We are writing this equation because to identify beta, to estimate beta. So gamma is just a sidekick. It's not important. It's purely nuisance parameter. If you know gamma, then it plays no role. Just it only causes trouble. Therefore, you may write it this way. Just if you know gamma, you can calculate beta. So the main parameter is always beta in this form, and gamma is something you have to overcome. And the first order condition, it can be written in this way. Again, this form is important because we start our asymptotic normality derivation from this. So from this, you Taylor expand and you do many things. And then, like, this function can be written in this way, and its derivative with respect to beta can be written in this way, and with respect to gamma in this way. By the way, I am going quite fast because you can do it by yourself. The algebra is nothing new. It's simple, just tedious, cumbersome differentiation and like adding and subtracting things. So you have to verify everything by yourself. Otherwise, it won't help at all. So I explain as if everything is obvious, everything is so simple, but if you try by yourself, it's not. So please make sure you try, you do the math, do the algebra by yourself. We learned all the theory in chapter 3. So anyhow, we have this function, which is going to be Taylor expanded and respect to derivative to beta, derivative to gamma. Everything is simple algebra. And from now on, let me simplify our notation. So even though each of them is quite simple, but after combining all of them, it will become more complicated. So I will simplify the notation. W is the fitted value. W is the fitted value, gamma z, and U is the new error term. U is the new error term when you replace X with W. And U may be understood in this way. So Y minus beta 0 W, fitted value. Anyhow, so like pretty simple. So W fitted value, U is the new error term. And then it is simple like so. Then G, the function G, can be written as W times U. Because this is U, this is W. Easy. And the derivative G beta can be written as my expected value of W squared. And finally, G gamma can be written in this way using this result. We know that the instrument Z is uncorrelated with the new error term U. So think about G. G can be written this way, and you may bundle sum up some part, and that becomes U, which disappears. So in the end, you only have this much. So I try to simplify everything, and then remember the influence function for the second stage estimator was given by this form. This is what we derived in the previous video. And then apply, plug in, insert G beta. G beta is this, so like inverse 1 over that G beta, and G small g I was WU, and large G gamma is this, so write that, and phi also derived phi, influence function of the first stage estimator. So, so it's still it like tends to be a little more complicated, but you may cancel out a lot of things, and it's easy to see the finally it becomes very simple. So again, algebra is not difficult if you just follow, if you just fill the gap. There are many jumps and many gaps, so you have to see how they become this way in the end by yourself. Like do the math, do the algebra by yourself. So anyhow, this is the final influence function for the second stage, the final estimator. And then under the assumptions, reasonable assumptions, it implies that the asymptotic distribution of beta hat is equivalent approximately this. And apply the central limit theorem, and the asymptotic variance is variance of this influence function. So the influence function can be used to calculate the variance. And it can be also simplified by assuming the homoscedasticity. So if epsilon squared, the expected value of epsilon squared, conditional on z does not depend on z, then the law of iterated expectations, it implies sigma squared expected value of w squared. Do it by yourself, and then this is cancelled out by a term in the denominator, and in the end, the variance of the two-stage estimator becomes sigma squared over expected value of w squared. So I did it very quickly, but try it by yourself without reading this. So just use the previous results from chapter 3 and previous video and see if you can get to this point. It's not there is no serious math, but it's useful to learn, and you are going to use two-stage least square in the future. So anyhow, now let's interpret, so the result is simple. I'm going to give you some intuition behind it. First, remember the OLS variance was like this. If the OLS with one regressor has the variance in this form, so if you have demeaned variable x, then you get this form, and then it's the same structure, the same form. And the difference here is because we replaced x with its fitted value, the variance of the two-stage least square is also have the same difference. So x is replaced by its fitted value, and always this denominator is smaller than this denominator, because w is just a part of x, and you can show that. It's easy to prove this. So because w is just a part of x, so its denominator is small, which means the variance is large, which means the estimator is less accurate, right? So if OLS was possible, of course OLS is better. So if there was no endogeneity, you can do better by OLS. But because of the endogeneity, you cannot fully utilize x, but only utilize some part of x, so making your estimator less accurate, making the variance larger. So that is one simple intuition you can get from the result. And second, now gamma is written in, gamma can be written in this way. The numerator is covariance, denominator is variance. So you know the OLS coefficient gamma can be written in this way when you have single regressor. And then with this, and also think about the correlation coefficient between x and z. The correlation coefficient is defined in this way, which involves covariance and variances. And so the covariance, expected value of x and z, can be written in this way. then plug this and this into your variance, asymptotic variance. So W is gamma Z, and gamma replaced by this, and then expected value of xz replaced by this. Then in the end, you get this. In the end, you get this. And this also relates the two-stage least square variance to the OLS variance. So two-stage least square variance is OLS variance times something, but something is always greater than 1 because the correlation coefficient is always smaller than 1. So 1 over that is greater than 1. That means, it shows that the two-stage least square variance is greater than the OLS variance. They are equal only when the correlation coefficient equals to 1 or minus 1, which means the instrument is basically the same variable as the endogenous variable. So makes no sense. And also you can say that the higher the correlation between the instrument and the endogenous variable is, the smaller the variance is. So if this correlation is close to 1, your two-stage least square estimator will have smaller variance, right? It's obvious. And also, you can say what happens if the instrument is weak. If the correlation coefficient is close to 0, then it becomes near infinity. Then your variance, two-stage least square variance, will be infinity. So that's the weak instrument problem. That is another way you can say something about this formula. And third comment. In the third comment, now I'm going to compare what happens if you ignore the first stage estimation error. As I said in the previous video, it is an interesting example because, so like intuitively, if you ignore the first stage error, you have to get a smaller standard error because there was some error but we ignored. Then your your standard error should be smaller, but actually not, which is shown here. If you calculate the variance correctly, the influence function is given by this, as we derived earlier. But if you ignore the first stage estimation error, so if the first stage influence function is 0, there is no variance in the first stage, there is no error in the first stage, then the influence function will be simply this, and so if this is 0, you get this, and it equals to this. So the same format, but epsilon is replaced by u. And remember, u is epsilon plus beta psi. So u includes additional term, right? So like the first stage error cancels out some of the error, which is interesting. So if you just expand what the variance of this, then you can get this format. So still, the sign is not determined. It can be smaller or greater than this. So if you compare variances of this and this, like the sign is not exactly determined, but in most cases, unless this happens, this variance is greater than this one, and this condition is likely to hold. For example, beta 0, and if beta and the covariance correlation between two error terms have the same sign, then because you ignore the first stage error, you are overestimating the error, like a little bit counterintuitive. And even if the signs are different, still overestimation may happen. So very interesting observation, but as I said, this is not general. This is a special case, one of the rare examples where ignoring error overestimates the error. Okay, this is it. Thank you for watching. I'm going to continue. I will call it a lecture, and I will consider a general case in the next lecture. See you then. Bye.